hello. Just trying to verify that my stream is working okay here. Having a little trouble getting my whiteboard being read, so just give me one moment, please. Alright, I think it's up now. If you're able to type in live chat, I think there's 5 of you online right now. Could somebody just type something? Just want to make sure that it's enabled. Not looking good so far. Enable live chat. Enable slow. Great, awesome. Patrick, hope you're doing well. Okay, so I took your questions in that you posted on the classroom site. So there's a few problems that I'm planning to go over. And oh my goodness, that's dedication. Few questions that I'm planning on going over and a few topics that I'm going over. So let me just go over kind of my pre-planned questions first, give you an outline, and then if you have anything that you'd like me to add, you can put it into chat as well. So there were a number of questions on piecewise functions. So I'm planning on doing an overview on all of the stuff on piecewise. There were some questions on finding the range and finding the X and Y intercept. I'm going to go through all of that specifically as well. As far as textbook questions, the high priority questions that were asked by a number of people, which I'm going to go over in detail, were on page, maybe instead of doing the page number, from 7.1, I'm going to go through number 13. From 7.2, I plan to go through 2, 8E, 10C, and 11C. There's some other questions that were asked by a few people as well, and I might kind of circle back to that. So let me go through those concepts here first. If you have questions as I'm going through, just put them in chat. Hopefully my audio and video are coming through okay. I tried this an hour ago, and it was, a disaster. So hopefully this one will be a little bit less of a disaster. And I'm just going to start off by talking about piecewise functions a little bit. And let's just do a linear function to start out with. And I picked this function of y equals 2x plus 2 because it's going to graph very nicely. So without worrying about this absolute value, let's just look at the equation y equals 2x plus 2. So we can see pretty clearly that that's going to have a y-intercept of 0, 2. So if we make x equal to 0, we get y equal to 2 here. It has a slope of 2 over 1. So we can also deduce from that that there's going to be an intercept at negative 1, 0. And you can see that if you plug negative 1 in for x here, we're going to get 0 as well. So here is the equation of that line. That's the equation of y equals 2x plus 2. And you'll note that I drew the part on the bottom dash, and that's because we're going to talk about how this relates to absolute value in a moment. Now, if this were an absolute value function, we're not allowed to have anything below the x-axis, so all of our y values have to be positive. So it would really look like this. Well, what's this function? This function is what would happen if I took the bottom portion of y equals 2x plus 2. When I say the bottom portion, I mean the part that's below this x-axis here, and I were to reflect it. Oh, changed my pen here. All right, and I were to reflect it. What is the equation of that reflection? Well, it's as if I reflected it in the x-axis, and what that's going to do is it's going to change my y values from negative to positive. So if I took this equation and I were interested in the reflection of it, it would be as if my y values were changed from negative to positive. This would be the reflection of my original graph. But realistically, we want to solve this for y. So what happens is that that negative sign gets applied to everything on the right-hand side. So I have these two equations, this one and this one. And what I want to kind of figure out is, looking just at this absolute value function, when does the blue equation of y equals 2x plus 2 apply to the absolute value? And when does the red equation of y equals negative 2x minus 2 apply to the absolute value? And it applies in those parts that I pointed to here. So from this, we can build the piecewise function. Now, we're using piecewise functions in absolute values. This is just the start of your journey through piecewise functions. This is a pre-calculus topic, this is a calculus topic, this is a university topic, and it's going to kind of explode away from what we're doing in absolute value. Absolute value is just a good introduction to using piecewise functions. So, what is the case is that for everything to the right of this line, it's the same as y equals 2x plus 2. So y equals 2x plus 2 for everything to the right of that x-intercept, which is, was negative 1, was it? So x greater than or equal to negative 1. And for everything to the left of that x-intercept, it's dictated by negative 2x minus 2, so that's when x is less than negative 1. Now, maybe you'll notice that in this particular case, where I put this equals doesn't matter. Just make sure it only shows up in one of the two places. Think if you were a computer program and you wanted to determine what piecewise definition to use for that point, you would look for one of these two to follow. You wouldn't look for an ambiguous solution, which would be to follow both. We're going to be doing more questions that involve piecewise functions. I just wanted to kind of do a little overview of a linear one before I kind of go on to some of the other problems. Okay. My stream is a little time delayed when it's posts here. So if you have questions as I'm going through, please just put them in the chat. And when I see them, which will probably be a few minutes after that you post them, I'll make sure to reply to them. Okay, so let's start with some textbook questions. And from 7.1, there was one that was asked a lot, but I just want to start with, sorry, I'm just looking through my textbook here. I want to start with 5C. Even though this one was only asked by one person, so this is 363, number 5C. Sorry, only one or two, which were you referring to? I'll go through this question and then I'll take a look at your response there in a sec. So for 5C, this is the distance problem, and we want to find the distance from C to B. We have B, we have C. B is at negative 3.4. C is at 2.1. The reason I want to do this is because when I looked at the solution key, I noticed it was always subtracting the larger number from the smaller number. That's not necessarily the case. So if we want the distance from C to B, we could do this as 2.1 minus the location of B, which is a negative 3.4, which is the absolute value of 5.5, which is 5. But you could have also looked at this as the distance from B to C. Hopefully I got this right, okay? So that would be a negative 3.4 minus 2.1, which is negative 5.5, and the absolute value of negative 5.5 is 5.5. So you can see that the absolute value is going to be calculated the same way, regardless of which point you use to start and which point you use to the end. And the way this would be used in real life is you would typically always start from where you're going to and subtract where you came from. So it might end up being an absolute value with a negative, it might end up being an absolute value with a positive. But either one of those I think is fine in this case. All right. So by far, from 7.1, the question that was requested the most was question number 13. So let's go through this in detail. So this is about the Festival du Voyage. And we start at the beginning here. It mentions that there are 3 checkpoints. There's one checkpoint at 500 meters. There's a checkpoint at 900 meters. There's a checkpoint at 1600 meters. And then the whole race ends at 2 kilometers, which is the same thing as saying 2,000 meters. And we want to figure out the total amount of distance that was traveled, and they give us the voyage that this individual goes on for the trip. So the race organizer starts by going from the start point to 1,600 meters. So that's the first part of this journey. After that, they go back to 900 meters. That's the second part. And then they go to the finish line. That's part 3. And then after that, they drive back to 500 meters. Okay, so that's part 4. So we need to calculate this total distance as an absolute value function. So let's get started. So this distance number 1, what we're going to do for all of these is we're going to take the end point, so in this case at 1,600 meters, and we're going to subtract the starting value. So the first portion of this trip, so part 1, will be 1,600 meters minus 0. Then for part 2, they ended up 900 meters from the start, and they started 1,600 meters from the start. So this relates to part 2. Part 3, they ended up at the end from 900 meters. So there's part 3. And I'm going to have to squish this in here a little bit. And then they went back to 500 meters from the end of the race. So this is part 4. Okay, so continuing on a little bit, and I'll just scroll my screen. So 1,600 minus 0 is just 1,600. 900 minus 1,600 is negative 700. 200 minus 900 is 1,100. And this last difference is 1,500. So since we're doing the absolute value of each of these, this just ends up being 1,600 plus 700 plus 1,100 plus 1,500. And I added that up earlier. I got 4,900 meters. And it asked for it in meters and in kilometers. So kilometers would be 4.9 kilometers. So that's how we could take a word problem, rewrite it into absolute values, and then kind of use that equation in order to find our answer. And this is the same sort of structure, like I said, that if this was being done automatically, a computer program might follow, or things along those lines. Okay, so we're going to go on to 7.2 now. So we get a new page. This will be page 375. I just want to look at number 2. I only received one question on it, but I feel that this is a good question to solidify your understanding of what is actually happening here. We have the point, -5, -8. What would happen if that point was applied to an absolute value function? Well, it would be reflected in the x-axis here. So what's going to happen is the x-coordinate will stay the same. This will still be at -5. And the y-coordinate will change from a -8 to a +8. So it's not that both of these negative signs change to positives. It's that it's a reflection in the x-axis, so your y values change from a negative to a positive. And that's going to be important to have an understanding of as we continue along with some of the more complex problems in this chapter. So we're going to go to 8e next. I believe it was 8e that was requested. Yeah. Okay. Seems like I did B as well, but 8e was the one that was asked for the most. So 377. 8e. Temporary coffee pots. I think that's why my previous stream didn't go well. I wasn't regularly consuming coffee. Okay, so 8e is this function g of x equals absolute value of x minus 3 squared plus 1. And what we want to do is we want to take this function, we want to state the intercepts, and to find the domain and range. Just a reminder, if you have any questions as I'm going through, feel free to ask them in chat, and I will address them as I see them. But my first order is I'm going to go through a few of the homework problems, and then I'll answer any additional problems that you might have after that case. But if you have questions about the homework problems. Anyway, okay, let's go. Intercepts. So to find, well, let's start with the y-intercept because that's always easiest. So to find the y-intercept, our goal is to make x equal to 0. So we're going to take this function of g of x, or if you prefer y, and we're just going to solve it when x is equal to 0. So that's 0 minus 3 squared plus 1. So this ends up being -3 squared plus 1. -3 squared is -3 times -3, so that's 9. So it's 9 plus 1, which is absolute value of 10. This gives us 10. So what does that tell us about our y-intercept? Our y-intercept is at 0, 10. All right. X intercept. So this is where this question gets interesting. To find the x intercept, we want to make y equal to 0. So let's take g of x and set it equal to 0. So that will give us 0 is equal to absolute value of x plus 3 squared plus 1. And as I went over in one of the lessons, that's the same thing as this. 0 equals the, x plus 3 squared minus 1, because it doesn't matter whether the 0 is negated, it's not going to change anything after that. All right. Well, thinking back to your quadratics, this is in an excellent state for us to use completing the square on. So if we subtract 1 from both sides, we get -1 equals x plus 3 squared. And now we want to solve this for x. Yeah, x. So we're going to take the square root of both sides and ensure that we do plus or minus over here. So on the right-hand side, we have the square root of x plus 3 squared equals x plus 3. And on the left-hand side, we have plus or minus the root of -1. Okay, so the root of -1 is not going to give us any real answers. So there are no real solutions to this problem. What does that mean? Well, we're trying to find the X intercepts, so we do not have any X intercepts. So this quadratic does not touch the x-axis. Okay, so stick this in your head for a moment. I'm going to go to a new page. So let's just write down what we have been working on. So we have g of x equals absolute value of x minus 3 squared plus 1. We had a y-intercept at 0, 10. Promise that was intended to be a 10. And we have no x-intercepts. So what that means is we're going to end up with a quadratic that looks like this. And we know with certainty it's going to be above the x-axis because of these absolute value bars. All right, so what we need to do is we need to find what the vertex is. Well, what do you know? This quadratic is in vertex form. Vertex form, if you recall, from those happy days in your mathematics classroom, is this, where the vertex is at PQ. So let's compare that to our g of x equation, which is x minus 3 squared plus 1. That implies that we're going to have a vertex at 3, 1. Okay, now we can finally sketch this graph and answer the questions about the domain and range. So 3, 1. I have done a poor job of drawing this to scale, but we have 0, 10 over here. So we're going to have a quadratic that looks something like this. Not asked for in this question, but we also know that the point 6, 10 must exist on this graph. So why do we know that? We have an axis of symmetry here through the vertex. So if we go 3 to the left and we get to 0, 10, going 3 to the right also has to get us to a y value of 10. Okay, not needed, but interesting. Now let's answer what they're asking for. So domain, well, this is x is an element of the real number system. Range, y such that y is an element of the real number system, and our y value is going to be dictated by this vertex right here. So y must be greater than or equal to 1. So this one is perhaps a little bit different than some of the other problems that were assigned to you, in which this quadratic was kind of resting along the x-axis. And we're going to go on and do one of those problems next. We're going to go on to 10C in just a moment. This is my fancy notebook where I worked everything out before the call. I have 8B on the list here as well, but I think I'll do, 10E maybe? No, 10C. So I'll do 10C, I'll do 11C. If there's any questions after that, I can go back to it. All right, so we are now on page, wow, that was a P, yeah. Page 377. 10C. So what piecewise function would you use to represent the graph of the absolute value function? So this was y equals absolute value of 3 times x minus 2 squared, subtract 3. And I'm going to do a very rough graph of the function that is in the textbook. Something like that. So this is all given to you in the problem. And what you're asked to do is to find the piecewise function. So I find the best strategy for figuring out the piecewise function is to figure out what does the quadratic look like if there are no absolute value functions. Because part of this will follow this quadratic, and part of it will follow its reflection. Well, observing this, where's the vertex of this graph going to be? This is in vertex form. So if it's in vertex form, it's going to be at 2, negative 3. So for the original quadratic, before the absolute value sign was applied, it had a vertex at 2, negative 3. What that means is that our original quadratic was this. And then the absolute value sign took the part with the dashed dots and it reflected it like this. So what that reflection is going to be is the y values are going to change from a positive to a negative. And if we put a negative on the left-hand side, we could just multiply both sides by a negative to move that over to the right-hand side. And I'm just going to get rid of that there. So that will mean that this blue portion is y equals negative 3 times x minus 2 squared plus 3. So notice that I just multiplied through the stuff that was on the right-hand side by a negative. So now we're going to write the piecewise function that's going to dictate this graph. So the part that's in blue is going to be described by that blue equation, and the part that's in red is going to be described by that red equation. And I apologize if you're colorblind, but to be fair, I believe that red-blue colorblindness is one of the rarest forms of colorblindness, as I learned in my research for my computer science courses that I taught. Okay, so let's look at the red part. So 3 times x minus 2 squared subtract 3. So when does that affect the graph? It affects it here and here. So when x is less than or equal to 1, or x is greater than or equal to 3. So for those parts that I have colored in red, it's dictated by 3 times x minus 2 squared minus 3. For the parts that I have colored in blue, it's dictated by the reflection of this graph. So that's between 1 and 3. So 1 less than x less than 3. Notice that I did not put equal signs here because the equal signs are already present in my other definition. So that would be the piecewise function that would define 10C. Although it wasn't asked, just for kicks, let's do the domain and range of this function, since I had a general question about domain and range for these piecewise functions. Now, your domain is always going to be, don't want to say trivial, but it's always going to be the easiest one. So x, such that x is an element of the real number system. Your range, however, if we look at this graph and look at the stuff that I have colored in, the part that is affecting the range is this. As long as it's above this x-axis, then everything is fine and it is defined for that graph. Note that that's different than the previous one that we looked at, because the previous one did not touch the x-axis. So our range, y, such that y is an element of the real number system and y is greater than or equal to 0. So it's just dictated by whether or not it's touching that x-axis. Okay. Last requested problem was 11C. And then if you have any other questions or additions that you'd like to make at that point in time, I'll be happy to hear them. I mean, you can make questions and additions right now. I don't care. But I'm doing this one. So 377, 11C. So express each function as a piecewise function. So 11C is y equals the absolute value of negative x squared plus 1. All right. So as I mentioned, when we're trying to figure out these piecewise functions, or when we're trying to figure out what a graph is, I find that the best place to start with is, what does y equals negative x squared plus 1 look like? Would you believe that this one is also in vertex form? This form of a times p, oh goodness, you saw nothing, x minus p squared plus q, which has a vertex at pq. The vertex for this problem is at 0 and 1. And note that we have a reflection, so this is going to open down. So we know the vertex is at 0, 1. 0, 1. So there's my super fancy graph. 0, 1. Opening down. We need to figure out what the X intercepts of this graph are in order to properly figure out where this graph is going to reflect. So to find the X intercepts, we make y equal to 0. So we have 0 equals absolute value of negative x squared plus 1. Right. Negative x squared plus 1. So if we just rearrange this, we get x squared equals 1. Next step would be to take the square root of both sides, ensuring that we do the positive and negative square root on the right-hand side. So x is equal to plus or minus the root of 1. So that means that, more specifically, root of 1 is just 1. So that means we have negative 1, 0. And 1, 0. All right. Okay. So, cool. Thanks for letting me make that mistake. Nice. Solid. Okay. So, negative 1, 0. 1, 0. So, this graph right here is this. And then, since this is an absolute value function, this portion that's below the x-axis is going to be reflected. So the equation that dictates the red portion is negative x squared plus 1. So that means when we reflect it, we're going to multiply y by a negative, which has the end result of we can keep y positive and negate everything on the right-hand side. So y equals x squared subtract 1. would dictate the blue portion. And you can kind of see that x squared subtract 1 would have a vertex down here. All right, piecewise time. So y equals. So it is this red portion, negative x squared plus 1, when x is between negative 1 and positive 1. And it is this blue portion, the reflection, x squared minus 1, when x is less than a negative 1 or x is greater than a positive 1. By the way, you'll note that I tend to put the reflection on the bottom and the original on the top. It doesn't matter. If these two are the other way around, it's fine. If these equal signs are the other way around, it's also fine. So there's no requirement there one way or the other. And that's all the homework. So if you have any additional questions, please type them in the comments. I'm going to drink some coffee. If I don't get any questions, then we will call this a day. Well, I guess we won't call it a day.